Hey there, friends. It's your favorite friend, Ham Young, here to talk about a recent breakthrough in the world of physics. Have you heard about the quantum holographic wormhole created inside a quantum computer? No. Well, let's dive in and explore the world of quantum mechanics and general relativity and how they relate to this fascinating topic. First of all, let's talk about the two main theories that describe the universe: quantum mechanics and general relativity. Quantum mechanics explains the physics of the very small, while general relativity explains the physics of the very large. The problem is that these two theories are not compatible with each other, which makes it difficult to create a unified theory of quantum gravity. In the 1930s, Albert Einstein and Nathan Rosen published the paper, in which they developed the concept of a wormhole called an Einstein-Rosen bridge. This wormhole consists of the extreme spacetime of two black holes connected via their singularities in a tube-like structure of spacetime. At the same time, they also published the EPR paper with Boris Podolsky, which argued that quantum mechanics is incomplete due to quantum entanglement. In their work, they introduced the concept of a wormhole, a hypothetical tunnel-like structure that connects 2 points in spacetime, possibly even in different universes or dimensions. The Einstein-Rosen bridge, as they called it, was a particular type of wormhole that connected two black holes via their singularities, the infinitely dense points at the centers of black holes. At the same time, Einstein and Rosen, along with Boris Podolsky, were also exploring the phenomenon of quantum entanglement, a strange property of particles in which the state of one particle instantly affects the state of another particle, no matter how far apart they are. This led them to propose the famous E-pair paradox, in which they argued that quantum mechanics was incomplete because it seemed to allow for faster-than-light communication through entangled particles, violating the principle of causality in relativity theory. So, in summary, Einstein and his collaborators were exploring two related but very different topics: the structure of space-time at the very large scale and the strange behavior of particles at the very small scale. The concept of the bridge and the E-pair paradox were both attempts to reconcile these two theories and develop a more complete understanding of the universe. In 1997, physicist Juan Maldacena proposed the idea that two entangled particles far apart could exchange information instantly because they were connected via a wormhole. He later showed that a system involving two sets of entangled particles was mathematically equivalent to two black holes connected via a wormhole. This led Maldacena and physicist Leonard Susskind to propose the EP-pair conjecture, suggesting that entangled particles are connected via a wormhole. Fast forward to today, and a team of physicists led by Maria Spiropulu of CalTech has created a quantum holographic wormhole inside a quantum computer. How is this accomplished, you ask? Well, according to general relativity, introducing anything with mass or energy into a wormhole would immediately close it due to its gravitational effect. But in our quantum system, negative energy can be simulated by manipulating the electrical field to change the spin direction of the qubits. The researchers created an entangled state between two sides of a quantum system using 7 qubits, consisting of 7 pairs of entangled particles. One set of particles acted as the entrance of the wormhole, and the other set acted as the exit of the wormhole. 2 more maximally entangled qubits were used, bringing the total to 9. One of these qubits is called a probe, and the other is called a reference. The probe was swapped out with a particle located at the entrance of the wormhole. That probe's possible states then quickly got entangled with the states of the other particles at the entrance, spreading or scattering its information among them. This is roughly analogous to a particle entering the mouth of a wormhole. Next, the experimenters changed the electric field to simulate negative energy to keep the wormhole open. The scrambled information from the probe was then transferred to the exit of the wormhole, consisting of the 7 particles on the other side. And then it unscrambled and focused on a single particle at the exit side of the wormhole. The researchers confirmed that information was transferred by measuring the amount of entanglement between the reference qubit and the particle at the exit. The surprise is not that the message made it across in some form, but that it made it across unscrambled. Now, before you get too excited, let me remind you that this is a quantum mechanical simulation of a wormhole and not a real wormhole in spacetime. We are still far away from creating a wormhole in spacetime.